Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I think we'll go ahead and get started with the next session. I hope everybody had a good lunch. There's probably still a few people finding their way back, but I think we'll get started. So we have a few talks in this session that are on a variety of different NLP topics. So our first speaker is Mader Lair, who's going to be talking about duration, features, and speech recognition.
Okay, hi. So I'm going to talk about discriminatively estimated joint acoustic duration and language model for speech recognition. And this is a work I am doing with Isaac Shafran. So in current speech recognizers, the parameters of the components are estimated independently. What I mean is that the parameters of the acoustic models and the language models are independently estimated. Consider the finite state transducer representation of the discriminative language model, where the paths represent the word sequences and the weights represent the probabilities. These probabilities are estimated with maximum likelihood estimation or with discriminative modeling. Similarly, the lexicon is a deterministic mapping from words to fonts. It may have weights representing different pronunciations of a word, but these weights are also estimated independent from the language model and the acoustic model. The acoustic representation of the allophone sounds are done with hidden Markov models. Hidden Markov models represent the temporal variability of the speech with the transition probabilities in a fixed linear left to right topology, and the spectral variability of the speech with the observation models. The observation vectors have a dimension between 39 and 50 dimension, and the state transitions are bidimensional. This high dimensionality of the observations make the contribution of the state transitions, state probabilities not relevant. Transition probabilities implicitly encode duration, so duration probabilities are usually ignored in most speech recognizers. As you will see shortly, we estimate the weight of the transition probabilities, but we didn't change the observation model. Duration information is useful, for example, to improve the performance of the speech recognizers in noisy environments. Prosodic features are more robust in noisy and channel variations. And it can be also useful with languages where duration plays a crucial role to discriminate between words. Font duration is important in the comprehension of speech. For example, in Arabic, the phonemic lengthening discriminates minimal pairs. For example, in this case, hal and hal. Or also in English, is very useful to discriminate between several words, like set and sit and ship and sheep. There are many studies in the literature that have add duration information. Some approaches are extensions of the HMM technique. So in hidden semi-Markov models, they replace the self-transition probability A sub II with a duration distribution. In the inhomogeneous hidden Markov models, not only the self-transition probability A sub II, but also the transition probability S sub ij depends on the duration distribution. And in the expanded state hidden Markov models, they represent each of the hidden Markov model state with another sub HMM model. In this and in that way, they increase the parameters. These approaches haven't been adopted because they are computationally expensive, because we cannot apply anymore the standard training and decoding algorithms, or because we are adding more parameters to estimate. And furthermore, the improvements that they observed were very limited. Another approach is the post-processing technique. People have used this approach modeling the duration at word level, and then using this information to rescore the output of the speech recognizers. But this approach is not efficient for languages with large vocabulary like Arabic. To set the context of the talk, consider the finite state transducer representation of the speech recognizer, where it can be seen as a composition of different finite state transducers. And the decoding graph is it can be made compact with standard FST operations like determinization and minimization. So G is the language model that defines the context dependency between words. L is the lexicon that maps words into fonts. Then the context dependency tree maps the fonts into the allophones. And finally, HMM are the acoustic representation. There are several recent papers that have addressed the issue of jointly estimating the parameters of the acoustic and the language models. In the first work, they adjust the weights of the decoding graph after composing the acoustic and the language models. But this approach is computationally expensive. And in the second and the third work, they maps multiphone units into utterances. In the first one, using segmental conditional random fields, and in the second one, using maximum entropy approach. These approaches have been tested in constrained tasks. So to motivate our approach, consider the word lattices that output the word recognition. The task of the scoring system is to pick the best hypothesis, the one with the lowest cost. But this hypothesis doesn't always match the oracle hypothesis, the hypothesis with the minimum word error rate. The speech recognizer makes systematic errors that the language model doesn't consider, and the discriminative language model compensate these word level errors. So in a finite state transducer representation, this can be seen as composing the output lattice with the discriminative language model, then projected to the output side, then collapsing the paths, and finally picking the best hypothesis. However, the finite state transducers that output the speech recognizer don't only contain word sequences. They also contain acoustic state sequences. So what we propose is that instead of ignoring that information, to take it as an extra information to build the discriminative models. So in a finite state transducer representation, this could be as composing the lattice with two discriminative models, one on the output side and the other one on the input side. The resulting transducer is projected to the output side. We collapse identical paths, and then we pick the hypothesis with the lowest cost. So in this case, we are applying the correction both on the input side and on the output side. So from the word lattices, from the finite state transducer, we can extract word sequences and also state sequences with at each time stamp. These sequences are usually represented as n-gram subsequences. So, for example, bigrams on word sequences and unigrams on the state sequences. And what we do is to estimate the weights that represent the context dependency between words and the weights that represent the context dependency between the transition probabilities. Another feature that we can easily add is the duration. We can, for large vocabulary, the speech recognizer provides a duration at word and subword level. And for large vocabulary tasks, to model duration at word level is too sparse because we don't have enough occurrences of each word to model representative distributions. At font level is too coarse because we don't have enough symbols to model many variations. So to model duration at cluster state level is a good trade-off. We encode duration in two ways, as counts and as indicators. As counts, we take into account how many times a feature appears within the utterance. And as indicator, we take into account the presence or absence of the features. So consider the following cluster state sequence, where the state 1000 with duration 2 appears twice. So in the count case, the feature for state 1000 with duration 2 will have the value 2. And in the indicator case, will have the value true. However, representing the duration in this case has a limitation. So consider, for example, that this distribution models the duration of an state in the training data. And as you see, the state with the duration 6 doesn't have any occurrence in the training data. So we can, if we model the duration with continuous distribution, we can apply like some kind of smoothing and avoid this. As first experiments, we model the duration at HMM state level. So for each font segment, we model a duration distribution. Here in this graph, you can see the empirical distribution of an state, and then when we fit this empirical distribution with the gamma distribution and the log normal density function. People usually have used gamma distribution to model duration at the state level, but it seems that log normal distribution is also a good choice. To extract the features from the continuous duration modeling, we have to do some kind of quantization. So our approach is to divide the duration distribution in 3 regions. One region will contain durations with low probability. Another region, the durations will have like a middle probability, and then a third region with the high probability values. Global linear models have been successfully used in discriminative language modeling. The decoding task in the speech recognition maps the input utterances x to a word sequences y. Gen of x is the function that enumerates the candidates for an input x. The representation phi maps each pair xy to a feature vector and a weight vector. In our case, the feature vector will have acoustic duration and lexical features. Then f of x is the output of the discriminative model. And we use the perceptron algorithm to model to build the discriminative models, because even with large feature space, it converges quickly. So in the perceptron algorithm, we penalize the features of the best hypothesis that doesn't match the oracle hypothesis, the hypothesis with the minimum Gore error rate, and we reward the features of the oracle hypothesis. Actually, we use the average perceptron algorithm to avoid the overtraining, and we didn't add the baseline score to the training because maybe it could dominate other features. So what we did is to interpolate the score of the baseline speech recognizer with the output of the discriminative model using an interpolation weight. We test our task in the Gale Arabic transcription task with 200 hours of Arabic broadcast conversations, and we decoded the data using 20-fold cross-validation. We tested in DEVO7 and Evaluative, and the acoustic models of the baseline speech recognizers were trained with 1,000 hours of data. The font set contains 45 fonts, including the long vowels, and the speech recognizer contains 5,000 clustered pentaphone states, including taking into account the word boundaries and the pauses in its context. And the language model has a vocabulary size of 737 CAG words and is a 4-gram language model. So for each weighted finite state transducer, we extracted 100 best unit hypotheses for the training and 1,000 best unit hypotheses for the testing. Here you can see in the first row the results for the baseline recognizer. Then when we only build a discriminative model with lexical features using around 1.1 million features in the training and with an interpolation weight of 0.30, then when we add acoustic features, and finally when we include the duration features. We tested in the cross-validation set DEVO7 and Evaluative, and we observed a gain of between 1.2 and 1.6%. And the proportion of the duration features was much smaller than the lexical features. So then we applied the continuous duration models after fitting the duration distribution with the gamma and log normal distribution, and we didn't observe any gain. But looking at the features, we see that practically all the duration features from the test data appeared in the training data. So it's quite could be a reason of not having any gain. So as conclusion, we propose an extension of the discriminative language modeling using features of the input and the output side of the speech recognizer. And we got an improvement of between 1.2 and 1.6% with the discrete approach. And we didn't have any improvement with the continuous approach, but maybe because we didn't have many duration features in the test data that were not in the training data. So as conclusion, we can say that we have proposed a framework that overcomes the weaknesses of the hidden Markov models, modeling the acoustic state transitions and durations. And I want to thank Brian Kisbury from IBM for providing the tools, and Brian Rowe for his feedback and his perceptron algorithms. Thank you.
Okay, so we have just under 10 minutes for questions. If you raise your hand, I can bring the microphones around.
Just a simple question first. On your first results slide, there was a distinction that I didn't quite catch. Back one more, sorry.
Yes, here. Yeah.
Thank you. So the bottom two, what's the difference between phi sub d sub d of s equals or double equals?
In this case, we model we encode the duration as counts,
I see.
and in this case as indicators.
Binary indicator feature functions?
Yes, but we didn't have any significant differences in one or the other way of encoding.
Uh-huh. And you end up learning a duration for each of these 5,000 pentaphone states?
Yes.
Oh, okay. Interesting.
Well, normally when people did this discriminant training for speech tasks, they use gradient-based method for optimization rather than perceptron. I remember in IBM they used to have perception, the gradient method for training.
Yes, but here the feature space is quite big, so the training could be computationally quite expensive.
Okay, but I thought that you were doing gamma distribution or normal distribution.
You are referring where when I model duration with a continuous distribution.
Uh-huh. So in that case,
but
it'd be more sensible to use the gradient method for the training, right?
I don't catch what.
So you learn the parameters of the gamma distribution and log normal distribution. Do you do that?
What I do is to fit the empirical duration distributions of the HMM state with the log normal distribution and the gamma distribution.
Okay, and then you use that as the model?
Extract from there the features to train the model with the perceptron algorithm.
Okay, so it's still discrete.
Yes, you have. We do a quantization after modeling the duration.
Oh, I see. Okay, I think the more reasonable approach is to use that as the model directly and then learn the parameters for those distributions, and that probably should be compared with that.
Okay.
This kind of
I
learning.
think it's a hybrid discriminative generative model, right? Where you're reweighting the output from some generative model. And the perceptron procedure is trying to learn a weight over that, maybe the log probability from your generative model? Either the probability or the log probability?
No, we are using a linear approach.
So this, next, sorry.
So we are using there a linear.
Yes, but your theta sub d, can you go back to slide 19? So that theta sub d sub gamma s equals n, that means you're including a feature, which is the log probability of the duration according to a gamma distribution, right? And then you reweight that log probability using perceptron. Does that sort of answer your question, Lee?
Yeah, I see. Okay, good.
I can show you have worked with Arabic, which is very rich in terms of durational minimal pairs. Is there an across-the-board advantage of your method to other languages, like, say, English, where durational minimal pairs are like almost rare?
This is something that we have in mind, that to try this approach for English, for example, and see if we will have any considered significant gain. Maybe here we got this significant gain because of the nature of the language. Yes, you are right.
We have time for one or two more questions. One thing I was wondering about with your data set, so it said Arabic broadcast conversations. I was wondering, is it like purely spontaneous speech one, where it's actually people like conducting an interview, or is it partly prepared speech, a combination, or?
Conversations are like phone calls, I think. Phone conversation.
So it's not like prepared news speech, like meetings, it's spontaneous.
No, this is spontaneous.
Any final questions? Okay, well, let's thank our speaker again. Okay, so the next talk is going to be by Nicholas Fitzgerald on summarization of evaluative text.
Okay, hello. So I'm going to be talking about a system I developed called Assess, which is Abstractive Summarization System for Evaluative Statement Summarization. So automatic summarization, the goal is to determine and express the most relevant information from a large collection of text. And this is dealing with a problem that's familiar, I'm sure, to a lot of us, information overload. So for instance, if you search the web for automatic summarization, you might get 85,000 pages, or best digital camera over 38 million. And obviously, no one can read that much, except maybe a grad student. But so specifically for this project, we're working on reviews. So for instance, on Amazon or a website in Canada, dinehere.ca, you might have reviews on a digital camera or a book or a restaurant. Or blogs, there's lots of opinions being expressed, or message boards for things like stocks. There's a lot of opinions out there that could be useful for various tasks. So this system, as far as we know, is the first fully automatic abstractive summarization system to complete this task. All the various parts existed, but this is the first time they've all been put together. And I managed to make an improvement over one of the steps of the pipeline. And so far we've done preliminary testing on a wide range of different domains, such as restaurants and digital cameras, video games, etc. So just before I get into how this works, here's an example summary. This is for a restaurant in Vancouver. And as you can see, it's summarizing based on various aspects of the dining experience, like service or the food, the price, the food, etc. So there's two main approaches in automatic summarization. The more traditional one, which has been pursued, is extractive summarization, which is where sentences are extracted from the source input text. And this is generally easier and faster, partly because it can be framed as a binary classification problem. But the problem is that the summaries can lack coherence, and it's difficult to aggregate information effectively. So the approach we take in this pipeline is abstractive summarization, which is where we first extract information into an internal format, and then we use natural language generation to generate new sentences expressing that information in a cohesive form. So in this way, we can get better aggregation and more coherence. So here's an illustration of the difference. With an extractive summarization, you might have two sentences expressing contrasting opinions. For example, I thought the battery life was more than adequate. We liked the camera, but the battery ran out too quickly. And obviously, this doesn't make very much sense if you read it in that order, whereas with an abstractive summarization, you could say something like, users had contrasting opinions about the battery life. So again, the pipeline is to extract the information into internal data format and then generate a summary. And for this project, our lab already had a natural language generation part of the pipeline, so I was mostly focusing on the data abstraction. So one other input to this system, which I'll explain its use later on, is a user-defined hierarchy. So this is a hierarchy of the features of the product that are important to the user of the summarization system. So for a digital camera, it'd be things like convenience, battery life, picture quality, etc. And for a restaurant, it could be things like service, ambiance, and then the menu items. So there's four main steps to the abstraction process. First, we're going to extract feature terms from the reviews. And at this point, we call these crude features because they're taken directly from the input text, and they can be using different ways to refer to the same feature. There can be spelling mistakes, etc. And for this, we used Hu and Liu. The next step is going to be to map these crude features onto that user-defined hierarchy, which was input by the user. So in this way, we can aggregate terms and we can reduce redundancy. The next is to evaluate the opinions being expressed in sentences. So we're going to assign a score to each sentence between -3 and +3, which is whether it is a positive or negative sentence. And then content selection and natural language generation will express this information in a summary. So for step one, the crude feature extraction, I followed an algorithm by Hu and Liu, which is based on the a priori algorithm for classification. It comes in two main steps. The first is to discover frequent features, which are words from noun phrases which commonly occur throughout the reviews. And then they have a step which supplements these frequent features with more infrequent features, which are noun phrases which co-occur with words which have been identified as sentiment words. So this step reduces precision but increases recall. So with this supplementation with the infrequent features, they reported a precision of 0.72 and recall of about 0.8. So for this step, it was more important to have high recall. I tested some other algorithms that had higher precision, but we want good coverage at this point because later on when we're mapping onto the hierarchy, we'll be able to reduce we'll be able to prune out a lot of the incorrectly identified features. So at this point, we have the sentences with the features identified here, highlighted in yellow, and we've extracted these features from the text. So what next? Now that we have these crude features, the problem is that there's multiple terms which can refer to the same aspect of the product, and there can be spelling mistakes and unfamiliar terminology. So one approach we could take at this step is basic clustering based on word similarity, but this can be quite prone to error, and the difficulty is even once we have the clusters, it's not necessarily, we'd have to then decide which of the crude features is the most appropriate to use. So the way we solve this problem is with the user-defined hierarchy. So what we're going to do is map these crude features onto the hierarchy like this, and then the terms in the hierarchy will become the ones used in the summary. And then one other thing is here at the head of the hierarchy, we have a node for any of the crude features which are not placed in the hierarchy, and that's how we can prune out incorrectly identified features from the previous step. So the mapping is an extension of synonym detection, and this is a step in which I did most of my work and managed to create some improvements. So the first thing to be done was I identified 13 word similarity algorithms which had been used, which fell into two main classes. The lexicon-based ones, which had been previously investigated for this task, and then I supplemented these with some distribution-based similarity metrics. So the lexicon-based ones are based on WordNet, which is a lexical database of around 150,000 English words. And it defines relationships such as hypernyms, homonyms, and synonyms. So the hypernym-based lexicon word similarity metrics are based on hypernym trees and are various metrics based on how far apart words are in this tree, based on height and path distance. And then the other class is gloss-based ones, which are based on word overlap in the definitions of the words in this database. So these are the 7 lexical ones used. And another important point is that since these are based on word sense, and because word sense disambiguation would be impractical in this step, we just assume that the word sense is with the maximum similarity. The other class of algorithm were the distribution-based ones. These are based on the assumption that words which mean similar things will occur together commonly in documents. So obviously for this we need a large corpus. And one technique that's been used recently is to use the internet, to use search engine hits in order to compute distribution similarity. So for example, there's this one based on pointwise mutual information and another one called normalized Google distance. So now once we have, and these are based on the number of hits for the 2 words. So now that we have these similarity metrics, first we need to normalize them between 0 and 1. And then, because these metrics are based on individual words, whereas the product terms could be multiple word terms, we're going to take a weighted average of the similarity between words in a term to get a score for similarity between 2 terms. And one benefit of the search engine metrics is that they can be used for entire terms rather than individual words. So you could search for the whole term, picture quality and image quality, rather than the individual word. So that gives us another 3 metrics to use. And then once we have this score between 0 and 1 for 2 terms, with the individual metrics, we say if the weighted average of similarity between a crude feature and a user-defined feature is above an empirically defined threshold theta, we'll map that crude feature to the user-defined feature. Now, in order to determine how accurate these mappings are, we have 2 main metrics which were useful. The first one is accuracy, and it's compared against a gold standard which was created by human annotators. And it's a measure of how far away on average a mapped crude feature is from where it should have been in the gold standard. So it's a score between 0 and 1, where 1 would mean a perfect mapping, where every crude feature is where it should be, and 0.5 means every crude feature is an average of one edge away from where it should be in the tree. The other one is recall, which only takes into account those crude features which were placed, so it ignores the ones that were in the not placed node on the tree. So preliminary results for the individual metrics, as you can see, they're all above 0.5, so they're all doing quite well. The first thing to notice is that the lexicon-based ones did much better than the distribution-based ones, so these new distribution-based search engines that I tested didn't work so well. They're all above 0.5. But the problem with all these individual metrics is that they require this empirically determined parameter theta. And so this LCH score was one of the lexical scores, and it achieved the highest, about 0.788. But as you can see, it's quite sensitive to this parameter theta. If you go too far in either direction, the accuracy drops off quite a bit. But what's even more sensitive to theta is the recall. So this is a problem because we don't necessarily know ahead of time what the ideal value of theta should be. And one other thing I want you to notice here is that even with 0% recall, there's still quite high accuracy. The reason for that is because 0% recall means they've all been mapped to the not placed node at the height of the tree, so they could still be quite close to where they should be. So it's not enough just to look at accuracy, we want to look at recall as well. So I wanted to improve on this, so the next thing I did was to combine these classifiers with ensemble methods. So I used a standard voting metric where we created a mapping with an odd number, 3 or 5 or 7 of these previously defined metrics, with their parameter set to 0. So we have the highest possible recall for each of the individual classifiers. And then if the majority mapped a given crude feature to a user-defined feature, then we would keep that mapping. So this is the accuracy improvement with the best group of 3 for n equals 3 and n equals 5. So we've beaten any of the individual metrics in terms of accuracy by using a voting metric. And also, here's the improvement in terms of recall. We've also managed to improve on recall. So one other important thing about this is that there's quite a good pattern for determining what would be a good collection of metrics to use in voting. So although I just reported the top score for 3, there's this quite robust pattern where if you choose one lexical score, one distributional score, and one of these other scoring metrics, these are the top 10 n equals 3 voting groups. So even though these distributional metrics didn't work very well individually, they've allowed us to get quite a good improvement when we use it with these voting metrics. So now that we've completed these first 2 steps, the third step of the pipeline is that we need to determine the sentiments being expressed. So we want to determine semantic orientation, which is a score. We use a score between -3, and +3. So pretty good would be +1. Overwhelmingly awful would be -3. I'm yet to see a review that actually said overwhelmingly awful in it. Ideally, we'd like to do this individually for every product in a sentence. For example, a sentence like, this camera produces nice pictures, but the battery life is abysmal. You have a positive score for pictures, a negative score for battery life. Unfortunately, this sort of intersentential sentiment analysis is very difficult to do, and it's kind of one of the main problems that's being worked on now. So for the purposes of this pipeline, we made the simplification that we just take one score for the entire sentence. And if we had sentences that had both a positive and a negative score in them, we'd throw those sentences out. And in the data sets we looked at, that worked out to about 1 in 6 to 1 in 8 of the sentences. But the hope is that with enough data, it'll all average out. So to do this scoring, we used SoCal, which was a system developed at SFU by Kimberly Vole and Maite Talboda. And it uses a tagged lexicon of semantic words. And these are modified by linguistic traits such as negation and augmentation. So good might be in the lexicon with a score of +1, and very good would make it a +2. And bad would be -1, not bad becomes +1. And then the score for a sentence is a weighted average of this, of all the semantic expressions in a sentence. So now for a sentence, we have all the features in that sentence and a score between +3 and -3. And using the mapping that we determined, we can get a score for the overall user-defined feature. So for example, picture quality, we have the mapping of picture quality, images, and picture. So we have all these 3 scores from these sentences. Finally is the natural language generation step. And this was previous work in our lab. So content selection is based on the importance of a UDF, which is determined by how many reviews we're talking about that given feature. And then we compute the average opinion and a measure of controversiality, the degree to which users agreed on that given score. And then this is expressed in a concise, coherent form with links back to the source material. So here again is that example summary. So we have, it's expressing the reasons why people felt positive about this restaurant, because diners found the service to be good, because the customers had mixed opinions about the reservations, etc. And then if you click on these numbers in the HTML output, you'll get a link to a sentence expressing that opinion from the input. And then here is an example of a similar review on digital cameras. And one benefit of abstractive summarization is that you can use it, once you've extracted this data, you can visualize it in other ways. For example, this is a tree map visualization, which we also produce, which is a way of visualizing user opinions. Or also you could create a natural language generation component that was written in another language. So you could have a abstractive summarizer, which was also translating. So the contributions of this work, again, was the first time that all these elements had been put together in a completely working pipeline. I was able to improve on the mapping step of Crude features, and so far it's been successful in preliminary testing on quite a wide range of domains. And there's clear avenues for improvement. Obviously, future work, I'd like to work on the fine-grained sentiment analysis, intersentential. And we'd like to improve the expressiveness of the natural language generation component so we could capture more information and improve the overall performance of the pipeline. So I'd like to thank the lab, and there are my references. Thank you very much.
Okay, thanks. So yeah, we have lots of time for questions, so I'll bring the microphones around.
Hi, I just had a question. When you were doing the summarization, did you start with topics in mind, or did you find documents without any necessary topic or type of sentence to start from?
I'm not sure I know what you mean.
Well, for instance, when you are doing the summarization of restaurants in town, did you look for all the restaurants in town? Did you look for that specific restaurant in town?
Oh.
Did you start off with compare and contrast Chamber Belgian restaurant to XYZ restaurant?
No, the input for this was just the text from dinehere.ca, specifically just for one restaurant. So we're looking to summarize the opinions about one specific product at a time. So you might have the input for one restaurant from dinehere.ca or for one digital camera from Amazon or something like that.
Also, then, if you went from a specific, did you try answering like a question from a specific type of sentence, or did you just use phrase searches like you would in Google or Bing?
Well, no. Well, we're looking to generate a summary about the whole reviews. But the topics that are mentioned in the summary come from the user-defined hierarchy that's input. So, like when it's talking about service and food and the ambiance, that comes from the hierarchy that's input.
That people thought.
Yeah. So if someone's only interested in one aspect of the product, say they only care about picture quality, you could just input that hierarchy with only picture quality, and then it would only summarize reviews which mentioned that feature.
There's one back in the corner here.
So, quick question about the section that you improved. So the WordNet syntactic similarities that you used. So Leacock came out the best.
Yeah.
Do you have an understanding of why that was particularly the best with your results? Because some of those are information theoretic measures, and others are graph measures.
Yeah, I didn't look individually at why one would be better than the other. I was really just looking to see how we could get the best possible mapping. So that's something to look at. Potentially we could improve that in the future. But
so another interesting solution to your Ensemble method might be to just run a quick learning algorithm over it to do a supervised method to actually choose the best combination of all those WordNet similarities that you've already calculated out.
Yeah. The problem with that is it might be domain specific, whereas we were hoping to get ideally something that would be unsupervised. So I was hoping that because we had this regularity in which voting metrics worked well together, then that could be used as sort of an unsupervised way of picking 3 that would work well or 5 that would work well.
Okay, there's one in the back corner here.
I had a question about the user-defined feature hierarchy. When you define it, are you defining one hierarchy, say, for digital cameras, and you try to make it generic enough to where it matches all the digital cameras on the market, or do you find that you have to do specific hierarchies for various types of cameras?
You can do either. That sort of depends on what user is using the system or what they wanted to get out of it. But so, for instance, there are websites that already produce these hierarchies for consumer reports, etc. But if you were interested in a specific product feature of one specific product, you could also add that to the hierarchy. For instance, when I made the hierarchy for the restaurant, I went to that restaurant and found their menu and put all the menu items on the hierarchy, so that if they had been mentioned in the reviews, they would be mentioned in the summary.
The reason I'm asking is about how easily does this scale? I mean, once you make this and say you want to apply it to lots of products out there, is there going to have to be a human involved that updates the hierarchy every time new products are added with new features?
No, well, I mean, if you're looking to compare, say, digital cameras, there's going to be features that are common to all digital cameras. But if you were looking at, say, a feature that only existed for a specific camera, you would have to add it to the hierarchy. But I found in practice that creating the hierarchy is really simple. It takes, and it's also a way of adapting the system to a specific user, because if one user maybe isn't interested in battery life, they want picture quality, or vice versa, or perhaps a less experienced user might not know what some of the features mean, so you could tailor it that way as well.
Thank you.
This is also on the feature hierarchy. I'm curious if any of your classifiers here or the Ensemble classifiers are sensitive to the number of features they're trying to classify things against, or are they all sort of just individual binary for each feature?
No, it was just, they're just mapping it to the user-defined feature, which is the most similar. So,
but if you have only one user-defined feature, then you might get more false positives than if you had 10?
Yeah, that's true. I haven't looked at that aspect of it.
I realize this may not be directly in your line of sight, but there's often a diachronic effect where with a new camera, I'm dissatisfied generally, but as I learn to use the camera, I learn that I love it. Mm-hmm. Is that anything that you're willing, or that you're looking at?
Well, I mean,
is one negative review just canceling out the positive review from that user, if they even make a second review?
Well, we're really looking just on how to summarize these kind of texts. So in terms of what you do with a deployed system to deal with that sort of thing, that wasn't part of what we're looking at. But I mean, hopefully with a big enough data set, enough reviews, the hive mind would come up with the right conclusion.
Question here. Hi, you had an illustration showing that showing a summary with, the customers of a restaurant having conflicting opinions about something or another. That's quite a sophisticated inference to make in a system which gets most of its mileage from information associated with individual words. And intersentential relations are important both in the extraction of discourse information process as well as in the generation process, I presume. Do you use, or will you find it useful to employ any sort of a formalism for capturing various types of relations between sentence fragments, like contrast and elaboration and support and implication and things of that nature? For example, like one might find common in rhetorical structure theory, which people use a lot in generation, I suppose.
Yeah. That's probably an important part of what we'll have to look at in order to do the intersentential analysis. Rhetorical structure theory is used in the generation part, obviously. But that's something we'll have to look at.
So your summaries look quite impressive for what they get out of words, presumably because it's used in generation a lot, right?
Yeah.
But presumably it'll be useful in comprehension as well.
Yeah, that's true.
We still have time for one or two questions, if there are any more.
Yeah, could you just tell us a little bit more about how you choose what to present in the summary? Because it's an abstractive summary, but I'm guessing you have a lot of choices. How do you choose what to say?
Well, I didn't work on the natural language generation part, but there's a measure of importance which is calculated based on the number of reviews which are talking about a specific node on the tree, and it also takes into account the measures of importance of its children on the hierarchy as well. So that way we can determine which features are more important. So ones which are higher on the hierarchy are given more weight. And then we're also looking to generate sort of a varied summary, so we want to talk about a wide range of features as well. So if you want to know more about the natural language generation part, you should talk to Dr. Karanini.
I assume that since you use a website like dinehere.com, people actually leave explicit scores, like stars on service and stuff. Can you use that to measure how successful your summarization is at measuring things like service and reservations and such?
Yeah, well, yeah, that's one of the ways we're looking at analyzing the overall success of the system, because yeah, like you said, people give scores. But problem is that those scores aren't very fine-grained. Right. They might give an overall score for service or food or value, whereas if you want to look at how successful the more individual features are, it's not so useful. But that's definitely something we're looking at.
So is there a strong correlation?
We haven't looked at that yet.
I often use the internet for looking at reviews of cell phones as they appear in Verizon or other, carriers' websites, and I'll get a lot of use out of applying your method to the customers' reviews of individual cell phones. Where phone comes out and within a month there are 2,000 reviews of it. I'd like perhaps like a super digest of these reviews using something like this, which is like a meta review from all those.
Yeah, that's the idea.
Any final questions? Okay, well, let's go ahead and thank our speaker. Okay, our next speaker is Shafiq Jody, who's going to be talking about topic modeling.
Okay, so I'll be talking about our research on exploiting conversation features for finding topics in emails. And I would like to thank Dr. Giuseppe Carnini, Dr. Raymond Ng, and Dr. Gabriel Murray. Now let's see why we are focusing on conversations. So, because nowadays in our daily lives, we experience with conversations in many different modalities. For example, we now have emails, we now have blogs, forums, instant messaging, telephone, video conferencing, etc. And the web has significantly increased the volume and the complexity. Now, effectively and efficiently processing of this media can be of great strategic value. For example, the email or the blog summary or the topic viewer can give you the direct and quick access to the information content. Now, before joining a meeting or before buying a product, a manager can have the summary of what has been discussed, or a customer can have an abridged version of the customer reviews. Now let's see an example of the email conversation from the BC3 corpus. Here you can see Charles is emailing to this mailing list about what the people that would be interested to have a phone connection to a face-to-face meeting. Then people who are interested, they reply to this email. Afterwards, Charles again emailed to the mailing list about the time zone differences. So here you can easily see there are two different topics in this conversation. Now let's see what do you mean by topic modeling here. So topic is something about who is the participants in a conversation discuss or argue. For example, an email thread about arranging a conference can have topics such as this location and time, then the registration, then the food menu, then workshops, and a schedule. In our work, we are dealing with the problem of topic assignment. That means clustering the sentences into a set of coherent topical clusters. Now let's see one example of this topic assignment on the example that we just saw. So here you can see first few sentences are in topic ID 1, then these two sentences are in topic ID 2, and here one thing to notice that the topic ID 1 can be revisited here. Okay. Now why do we need this topic modeling? So our main goal here is to perform the information extraction and the summarization for conversations like email or blogs or chats. And topic modeling is often considered to be a prerequisite for further conversational analysis. And the application of the drive structure are broad, encompassing this text summarization, then information ordering, then automatic question answering, then information retrieval, and intelligent user interfaces. Now, what are the challenges that we face when we are dealing with emails or other conversations? So emails are different from written monologue or dialogue in various ways. They are asynchronous, that means different people sitting at different places at different times collaborate with each other. Then they are informal in nature. Different people have different styles of writing. People tend to use short sentences and often they are ungrammatical. And the fact that topic does not change in a sequential way and headers can be misleading when we are going to find the topics in an email. Now let's see the example here. So you see this sentence, like the at least one people would. This person is quoting one of these sentences and he just wrote this sentence. It's a very short sentence, and if you just take this sentence individually, it does not bear any meaning. Again, here you can see Charles is using the same subject to talk in a different topic, which is a time zone difference. And here you can see the topic 1 is revisited. So here the assumption of topical boundary as in monologue or in dialogue is not applicable. So this is the example, short and informal. Headers can be misleading and not sequential. So the outline of the rest of the talk is, at first we will see the existing methods for topic modeling, then how the existing methods can be applied to conversations, then we will see can we do better than those, then the preliminary evaluation on a small development set, then we will focus on the current work that we are doing right now. So the existing methods in the literature. So topic segmentation or finding the boundaries in written monologue or in dialogue has got the most of the attention, and the methods can be one of these two categories. One is the supervised methods or unsupervised methods. In supervised method, the problem is just a binary classification problem where given the sentence break, you have to decide whether there should be a topical boundary or not, and they use a set of features. And in the unsupervised case, these are the two popular models. One is this lexical chain-based segmenter, another one is this probabilistic topic models, there is latent Dirichlet allocation. So we'll see how these two models can be applied to the conversations. Recently, for conversation disentanglement, this graph-based clustering method has been applied. Fortunately, there is no work in emails, so that's what we are trying to do. Now, at first, let's see how we can apply these existing methods to the email conversations. First, the probabilistic topic model, that is the latent Dirichlet allocation. So as you know, this is a generative topic model of documents where the assumption is that a document is a mixture of topics and a topic is a distribution, multinomial distribution over words. So to create a document, at first you select the topical distribution for a document. Then for each word in that document, you at first select the topic from this distribution, then you sample the word from that topic distribution. So in our case, each email is considered as a document, then given a distribution of words. LDA gives this a distribution of words over the topics. Now assuming the words in a sentence occur independently, we can just extend those probabilities to the sentence level probabilities, and we can just take the argmax to find the one on topic for this sentence. So this is how we applied the general LDA model on our email conversation. Now let's see the second model, that is the lexical chain-based approach. So you know, these lexical chains are the chains of words which are semantically related, and the relations can be this synonym, then the repetition, then the hypernym, then the hyponym. But the basic lexical chain-based approach, they just use this repetition relation. And the chains are ranked according to these two measures. One is the number of words in a chain and the compactness of the chain. The words in a chain are given, the score is same as the rank of the chain. Then once we have the scores for the words, we form the pseudo sentences of fixed length Then for is fixed window, or for 2 consecutive windows, we find the similarity measure between these 2 consecutive windows. If the measure falls below a threshold, then a boundary is given. So this is the traditional lexical chain-based approach. Now, as you have noticed that both LD and LC-SEG consider only the bag-about features. Though LC-SEG considers minimal structure, like the temporal relation between the emails, but it ignores other important features, such as the conversation features, then people mention names, this mentioning name features, and topic-shaped keywords like now, however, and the form-to relation. So example of these important features, here you can see that people often use this, people often quote sentences from other emails to talk to the same topic. And here you can see that people often use names to disentangle the conversation. So to find the topics, we have to consider these features. So what we need is capture the conversation at a finer granularity level, then consider all these important features, and then way to combine all these into a model. So let's see the way that we extract conversations from the emails. So we analyze the actual body of the emails. By analyzing the body of the emails, we find these 2 kinds of fragments. One is the new fragment with depth level 0, and another is quoted fragment, which can be depth level greater than 0. Then we form a graph where the nodes represent the fragments and the edges between the nodes represent the referential relation between the nodes. So it will become clear with an example. Just let's see the example. So here we have these 6 emails in an email thread. This email 1, it has only one fragment. There's on new fragment, this is A. Then email 2, it has one new fragment B, and it's replying to A. Then email 3 has a new fragment C, it's replying to B. Just for simplicity, we are assuming that a fragment can reply to its neighboring fragments. Now in E4, we have this DE replying to E, but until we process this E5, we don't know that D and E are 2 different fragments. So we have to find the different fragments in the first pass, then we form the graph in the second pass. So the result of this process is this graph where the nodes are the fragments and the edges represent the referential relation between these fragments. So once we have this graph, now let's see whether we can apply the existing methods on this graph or not. So we choose to use this LC-SEG on this fragment quotation graph and to test whether it improves the performance or not. So on each path of this fragment quotation graph, we apply LC-SEG and found the topics. Then to consolidate these results of different paths, we form a graph where the nodes are the sentences and the edge weights represent the number of cases where these 2 sentences U and B fall in the same segment. And we find the optimal clusters by the normalized cut criteria. So this is how we applied LC-SEG on fragment quotation graph. Now let's focus on our preliminary evaluation. So the evaluation metrics that we use, just note that the evaluation metric should be something that given 2 assignments of the evaluation of given 2 topic assignments, the evaluation metric should measure how much these 2 assignments agree. And here note that this widely used cup statistic is not applicable because we may have different number of topics in these 2 annotations. So what we did, we just adapted these 3 measures from this paper, Misha and Charniak, ACL 08, and it's more appropriate for this task. So this one is 1-to-1 measure, then log K measure, and M-to-1 measure. So we'll describe these 3 measures in the next few slides. So evaluation metric 1-to-1. This 1-to-1 metric, it just measures the global similarity by pairing up the clusters of 2 annotations to that maximizes the overlap. So here, for example, we have this source annotation. Here is the target annotation. So we at first map each of these clusters into one of the target cluster with which it has the highest overlap. So here you can see this is the source annotation. Then we have this optimal mapping. These reds are mapped to these greens. Then these blues are mapped to this white or something like this. So we have this optimal mapping. So the source will be now this, and then we measure the overlap between this source and target. And here you can see the overlap is 70%. So this one is correct, this one is correct, this one is wrong, this one is wrong, this one is wrong. So out of 10, 7 are correct and 3 are wrong. Then the log K measure, it measures the local agreement within a context of K occurrences. So here, for example, it's a sliding window protocol. So here you can see for this sentence we see like, okay, this is the source and this is the destination or the target. So for this sentence, we at first check the previous K utterances whether they are same or different. So for this it is different, for this it's same because this is red, this is red, for this is different. Same with the target one. So this is same, this is same, and this is different. Then we measure the overlap between these two mappings. Here you can see it's 66%. Then the fact that some annotations can be more finer grained than the others. So for this we use this M21 measure, and it maps each of the clusters of the first annotation to the single cluster in the second annotation with which it has the greatest overlap. And this measure gives us an intuition of annotator's specificity. But to compare the models, we should not use this measure. We should use this one-to-one and log K. Now for our evaluation, we are using this 5 threads from the BC3 corpus, and the inter-annotator agreement between these 5 annotators you can see. And we compared these annotations with the annotation of this Misha's paper, which is chat corpus. So you can see this one is quite higher than this one. This one is low. This one is kind of same. So it's kind of a feasible task to do. Now let's see the results of our 3 systems that we described. So here you can see this is the probabilistic LDA model, and this is the LC-seg model, and this is the LC-seg when we apply with fragment quotation graph. So here you can see this LC-seg is performing better than this LDA, and this LC-seg plus fragment quotation graph is applying better than this, is performing better than this LC-seg method. And the differences are significant. So right now what we are trying to do, we will consider, or this is the proposed solution, where we intend to consider a rich feature set for each pair of sentences, and we intend to use these features for the in the topic features. We have this LSA, there is the latent semantic allocation, latent semantic analysis, then LDA, latent Dirichlet allocation, and in the conversation features we have the distance between 2 sentences in the fragment quotation graph, and the speaker, then the mention of names, and in the lexical features we have this TA by IDF measure and the keywords. And our method is classify, which is supervised, and then cut. So we will use one binary classifier to decide whether given 2 sentences whether they should be in the same topic or not. Then we will form an unrated graph where the nodes will be the sentences and the edge weights will denote the class membership probability. Then the problem it becomes just the graph partitioning problem, which you can just solve using the normalized cut criteria. Thanks.
Okay, plenty of time for questions again. So if you put your hands up, I can bring the mics around. Yeah.
Yeah.
So I was wondering how on average, how many topics do you find per?
In the 5 email threads that we had, we found, I guess, 3.4 per thread.
Per thread.
Yeah.
And so you have 5 email threads to work on.
Yeah.
And did you have multiple people annotate
Yeah.
for the topics?
There are 5 annotators.
Okay. Did they find it hard to come up with the same set of topics, even if they, and even if they, kind of found the same span for a topic? Did they label it in the same way?
Yeah, they label it. And you see, for the clustering purpose, it has the problem like the label choosing problem. Like you can one annotator can have one cluster which is labeled as cluster 1, but the other annotator can have the same cluster as label 2. But we made the annotators write the name of the topic.
Mm-hmm.
So our results is something like this: the inter-annotator agreement. Here on the email corpus. So here you can see this is our, in one of the email there is 100%. They all agree. And this is the minimum agreement, and this is the mean agreement.
So if they named the topic, were the names that the annotators gave would that have helped the identification? I mean, I was wondering if the LDA models would predict what the names for the clusters should be. Just out of curiosity.
Yeah, but I don't think that LDA model is capable of doing that, because you can see the performance here is quite low.
Okay, other questions?
So then how often are people using the angled brackets to actually show that they are referring to different topics? So I mean the thing is that I actually don't use those in any of my emails. So I'm just wondering how reliable.
In our corpus it's people are using pretty often. Okay. So our corpus is the BC3 that we have at UBC. So people often use quotations. Yeah.
So email threads are so hard to come by, and you yourself have 5. Can we initiate some effort to try to collect more so that we can?
Yeah, we have 40.
This?
We have 40.
Okay, you have 40.
Yeah, but for this experiment we just tried with 5. It was a pilot study, so we just did it with 5. So right now we are trying to use all these 40.
Mainly list. So this BC3 corpus is from the Worldwide Web Consortium. So it's a mailing list, and we have lots of emails from this mailing list. There is no problem of privacy, or it's public. So the challenge is to annotate this data, but unlabeled data is available.
And one thing is that I was trying to incorporate this conversation structure into the LDA model as a prior. LDA model uses this for the document, for the topic word distribution, it uses one Dirichlet prior, right? So I was trying to incorporate this network structure into this model. So I came up with this an approach that will allow us to do this. So right now I'm kind of done with this. So as a machine learning project, I did this. Hopefully it will come up with some better results. So hopefully you'll see some papers over there. Okay.
Well, yeah, I was just going to ask about the sequential structure, because I think this is sort of what you were just talking about. Is it sounded like you weren't really modeling, like if you're talking about topic one, maybe you're going to continue talking about topic one in the next reply to the email. Is that, I think it sounded like you sort of weren't doing that, but that's sort of future work. Is that correct? Or?
Which one?
Oh, I mean, so if like the topic maybe will stay the same, like I'm just talking about the transition between topics.
Topics, yeah.
Yeah.
We are considering this problem as a clustering problem, but we have this LC sec feature, so which will like consider these features, like whether they occur together or not. So implicitly we are considering this feature.
Thanks for your talk.
Yeah.
One question. So do you have a fixed number of topics when you're running LDA, or are you using like a Chinese restaurant process to get an arbitrary number of topics? Is it not
no,
parametric?
for this we set the alpha parameter, that is the is very low, and we check the probability of z, that is the latent variable, whether it goes below below the threshold, and if it's below the threshold, then that topic is gone, like that topic is not there.
I see. So because looking at your results
here, it's kind of automatic cluster detection.
Right.
Yeah.
Right. Looking at your results here, LDA seems to do much better on M to 1 than it does on any of the other evaluation metrics. So I wonder if it's proposing too many topics?
I think, no. For this, we fixed the number of topics.
Yeah.
Like the number of topics is just the humans found in this conversation. So just to see like just to see the best output of LDA that one could get. But now I am trying with like this alpha very low in this parameter.
Thanks.
And just to tell you that the prior that I am using is Dirichlet tree, so it allows you to incorporate network structure. Yeah.
You might have experienced it too, but I often am part of email threads which tend to kind of gradually proliferate in such a way that each respondent diverges slightly from the original topic of the email to such a point that sometime further on, what you respond with has nothing to do with the original subject field, or maybe nothing to do with the topic at all.
Yeah.
Will you have a method of quantizing the relevance to the original topic in such a way that you can just filter out all the nonsense at some point of time?
Yeah, like we have this fragment quotation graph, right? So we are considering the the distance between two sentences in this fragment quotation graph. So if the distance is higher, then you are considering that there's a topic shift.
Okay.
Yeah.
Any other questions? We still have a couple minutes if anybody has a final question. I have one question. So you mentioned with the emails that so one of the issues is that people will sometimes revisit topics.
Yeah.
So that's not sequential. I'm wondering if you have a sense of how prevalent that is, and also whether this is the same in emails versus chats. If you've noticed any differences with how topic structure is realized in the two domains.
Chats, like in the multi-party chat, it's a different phenomenon, right? Because different people are interacting with each other, so there are many different conversations. But for the real chat, I did not check it because we do not have this chat corpus in the real chat. We have just this multi-party chat. But I think it's kind of more synchronous in chat, but in email it's asynchronous, so that's why like people can revisit thing out.
Okay, so if there's no more questions, let's thank our speaker again.